In this example, I'm going to be using the Exam.MTW dataset, which contains the quiz averages and final exam scores for 50 students. I'm going to use simple linear regression methods to construct a model using quiz averages to predict final exam scores. I'll be using the 5-step hypothesis testing procedure, but first, I'm going to use Minitab Express to get all of the necessary output. I'm starting with Minitab Express in this case because the first step of the 5-step hypothesis testing procedure involves checking assumptions, and in simple linear regression, you can't check assumptions until you've run the model to get all the necessary plots. The steps are the same with the PC and Mac versions of Minitab Express. Go to Statistics, Regression, Simple Regression. I want to predict final exam scores using quiz averages, which means that the final exam scores are the response or y variable, and quiz averages are the predictor or x variable. Under graphs, I need to select residual plots. This will give me all of the plots that I need to check assumptions. Click OK. This gives us all of the output that we'll need to conduct our test. I'll take you over to my PowerPoint slides now to walk through the 5-step hypothesis testing procedure. As a reminder, we are constructing a model using quiz averages to predict final exam scores. So quiz averages are the predictor or x variable, and final exam scores are the response or y variable. What we're really testing here is whether or not the slope is statistically significant. Step 1 is to check assumptions and write hypotheses. We have 4 assumptions: linearity, independence of errors, normality of errors, and equal error variances. We'll start with linearity. The relationship between the two variables must be linear. We check this assumption by looking at a scatter plot. I got this plot from Minitab Express. When you run a regression model, this will be the plot labeled fitted line plot for linear model. You can ignore the red line. Because we asked Minitab Express for a linear model, it fitted a straight line here. But what we need to look for in this plot is that the points should have a linear relationship, or at least not a nonlinear relationship. And that is the case here. If I were to draw a line of best fit, it would be a straight line, so this assumption has been met. The second assumption is independence of errors. This means that there is not a relationship between the predicted values and the residuals. We check this assumption by examining a scatter plot of residuals versus fits. This is the second plot that we got from Minitab Express when we ran our model earlier. On the x-axis, we have the fitted values, which is just the term that Minitab uses for predicted values, or y hat. And on the y-axis, we have the residuals. These are sometimes referred to as the errors. The correlation on this plot should be around 0. In other words, the line of best fit for the points on this plot should be a flat horizontal line. Minitab always draws a flat line on this plot regardless of what the trend is, so I'll cover that up so it doesn't confuse us. If we look just at the points, the line of best fit here would indeed be a straight horizontal line, so this assumption has been met. The third assumption is normality of errors. If we look at all of the residuals, they should be approximately normally distributed. We have 2 plots that we can look at to judge this. On the normal probability plot, we're looking to see if our observations follow the red line. If they all fall on or near the red line, this tells us that the distribution of residuals is approximately normal. We could also look at the second graph, which is a histogram of the residuals. Here, we want to see an approximately normal distribution. We're dealing with sample data here, so we don't expect it to be perfectly normal. In this particular histogram, it's close enough that I would call it approximately normal, and I would say that this assumption has been met. The last assumption is equal error variances. To check this assumption, we'll go back to the plot of residuals versus fits. This is the same plot that we looked at when we checked for independence of errors. Now what we're focusing on is the variability of the residuals. We want to see that the spread of the residuals is consistent over all of the fitted values. In this plot, the spread is approximately equal the whole way across the x-axis, so this assumption has been met. Now that we've checked all assumptions and they've all been met, we can finish step 1 by writing the hypotheses. We're using quiz averages to predict final exam scores. We were never given any information about a hypothesized direction. In other words, we were never asked if there's specifically a positive or a negative relationship. So we're going to treat this as a two-tailed test. What we're really testing here is the slope. The symbol for a population slope is the Greek letter beta. Our null hypothesis is that beta equals 0. In other words, the slope in the population is 0. That would be a flat horizontal line, which is what occurs when there's no relationship. Our alternative hypothesis is that beta does not equal 0. Step 2, calculate the test statistic. We'll get the test statistic from the coefficients table. The constant row is the y-intercept. But what we're interested in here is the slope, which is the row labeled as the x variable quiz average. The t-test statistic is 5.31. Step 3, determine the p-value. Next to our test statistic on the coefficients table is our p-value. P is less than 0.0001. Step 4, make a decision. Our p-value was less than the standard 0.05 alpha level, so we reject the null hypothesis. And step 5, state a real-world conclusion. There is evidence that students' quiz averages can be used to predict their final exam scores in the population.